Hello and welcome to this Python tutorial. Alright, so now in the next function that we're about to implement, we will train the deep neural network that is inside our artificial intelligence. So basically we're going to do the whole process of forward propagation and then back propagation. So that is, we're going to get our output, we're going to get the target, we will compare the output to the target to compute the loss error, then we're going to back propagate this loss error into the neural network, and using stochastic gradient descent, we will update the weights according to how much they contributed to the loss error. So let's do all this. For those of you coming from the deep learning course, this will be kid stuff, but for the others, don't worry, I'm going to explain that again. So we're going to call this new function learn, and this learn function is going to take several arguments. First, self, of course, which will refer to the object of the DQN class. Then we're going to take our batch state for the current state, then our batch next state, then our batch reward, and finally our batch action. So why do we take this? You probably recognized what is this series. Well, that's of course a transition of the Markov decision process that is at the base of DeepQ learning. And why do we all take them into some batches? Well, that's because, remember, we don't consider the transitions by a series of the tuple current state, next state, current reward, and current action. We created some sample batches here, thanks to the sample function. And so now our transitions are in the form a first batch for the state, a second batch for the next state, a batch for the reward, and a batch for the action. That's the form of our transitions now. And they're all well aligned with respect to time, thanks to this concatenation that we made here with respect to the first dimension. So the point is, now we have these transition of batches, one batch for each of the state, next state, reward, and action. And we do all this because we're using this experience replay trick so that our deep neural network can learn something. Remember, if we only had the transitions by themselves, well, it would be some instant learning, or if you want some very short memory learning, and therefore the model wouldn't learn anything. So we have to take these batches from the memory, which become our transitions, and then eventually we will get the different outputs for each of the states of the input batch state. And we will do this for the batch state and for the batch next state, because we will need both to compute the loss. I will soon remind the balance equation that is at the heart of the DeepQ learning algorithm. So now let's go into the function, and let's first get the outputs of the batch state. So I'm going to call this first variable outputs, and then we're going to take, of course, our self.model. So self.model, because we want to get our model outputs of the input states of the batch state. And since our model is actually expecting a batch of input states, well, we can totally input batch state right now for the input of the model. That's exactly how we initialized the states that are going into the network with a torch tensor with this fake dimension for the batch. So that's perfect. We now get the outputs of the model. But then there is another technical trick. If we only do self.model batch state, well, we will get the outputs of all the possible actions, 0, 1, and 2. But that's not what we want. We are only interested in the actions that were chosen, the actions that were decided by the network to play at each time. And so to get these actions we're interested in, that is the actions played, well, we have to use this gather function in which we input 1, because we only want the action that was chosen, and then we add batch action. With this, the 1 and the batch action, we will gather each time the best action to play for each of the input states of the batch state. We only want the action that is played, the action that is chosen. And we get this with this gather, 1, and batch action. But then be careful. The batch state here has this fake dimension corresponding to the batch, and batch action doesn't have it. Batch state has it because we used the onsqueeze here, but we haven't used any onsqueeze for the actions. So we have to add it here so that the batch action has the exact same dimension as the batch state. So we're going to add a dot onsqueeze 0 right here, And actually this is not 0 but 1 because 0 corresponds to the fake dimension of the state and 1 will correspond to the fake dimension of the actions. And finally, the last thing we need to do here is we need to kill this fake batch with a squeeze. And why do we need to do that? Because now we're out of the neural network, we have our outputs, but we don't want them in a batch, we want them in a simple tensor, a simple vector, a vector of outputs. The batch is just when we work in the neural network, because the neural network is expecting the format of tensors into a batch. But now we have our outputs, and in the next balance equation of the deep Q-learning, we won't need them into a batch. So I'm killing the batch here, I'm killing the fake dimension to get back the simple form of our outputs. So I'm just adding here dot and then squeeze. And then, since I want to kill the fake dimension corresponding to the batch of the action, well, since this fake dimension has index 1, I'm adding 1 here. Alright, and now, there we go, we have our outputs. Okay, we have a little warning, what is it? Local variable outputs is assigned but never used. That's okay, we will use it very quickly. So that's our outputs, and now we want to get our next outputs. So now you might be thinking, why do we need the next output? Well, to understand this, we need to go back to the Deep Q-learning algorithm, which is right here. That's a part of the LaTeX handbook. So that's the whole Deep Q-learning process. At the beginning, we're initializing all the Q values. And then at each time t, well, there we go. We select the action with softmax. That's what we did with the select action function. Then we append the transition. And then, as you can see, we get the prediction, we get the target, and we compute the loss. So why do we need the next outputs as well? That's because of the target. The target is equal to gamma times the next output plus the reward. And we will compute the target right after that. But since we need the next output for the target, let's compute this first. So again, to get the next output, that's very simple. The next output is going to be the result of our neural network when the batch next state is entering it as input. So very simply, we take our model, that is our neural network, and then this time, the input of the neural network is going to be the batch next state. The batch next state, but now remember, if we go back to the Deep Q-learning algorithm, well, you can see that the next output is the maximum of the Q values for the next state with respect to all the actions. So right now, to get the next output, we need to get the maximum of these Q values. And therefore, I'm going to do here a detach, to detach all the outputs of the model, because we have several states in this batch next states. That's the batch of all the next states in all the transitions taken from the random sample of our memory. So I'm detaching all of them using the detach function, and then I'm taking the max of all these Q values. And since we're taking the maximum of these Q values with respect to the action, well, we have to specify that it is with respect to the action. And since the action is represented by the index 1, well, again, we have to put the index 1 here. And then we have to specify that we're taking the Q values of st plus 1, that is the next state, and the next state is represented by the index 0, because the index 0 corresponds to the state, and therefore here we need to add brackets with the index 0. That way, we get the maximum of the Q values of the next state, represented by the index 0, according to all the actions that are represented by the index 1. And now, perfect, we get our next outputs. These are unused yet, that's why we had the warning, but that's fine, we will use it right now to compute the target. And speaking of the target, that's the next step of this learn function. So there we go, target equals, now let's get back to our AI handbook. The target is equal to the reward plus gamma times the next output. That is the maximum of the Q values of the next state according to the actions. So there we go, let's compute that. So that is equal to self.gamma, and self.gamma was initialized here. It is introduced, so that's a variable of our DQN object. Self.gamma times the next output, as we just said, plus the reward, that is the batch reward. We're working with batches here. So plus batch reward. And that's the target in one sample of the memory. gamma multiplied by the next output plus the reward. All right, perfect. So now we have our output, we also have our target, and therefore we can compute the loss. The loss that is representing the error of the prediction. So let's call this loss TD loss. TD is of course for the temporal difference. That is again at the heart of Q-learning. And this TD loss is going to be equal to the Huber loss. That improves much the Q-learning. That's the loss function we will choose for our artificial intelligence. For those of you coming from the deep learning course, that's really the loss I recommend if you want to implement deep Q-learning. And so how are we going to get this Huber loss? Well, again, we're going to take a function from the functional module, represented by f, and therefore here I'm going to use our functional module, f, dot, and the Huber loss can be obtained thanks to the function smooth L1 loss, that one. So pressing enter, and that's really the best loss function I recommend for deep Q-learning. It really improves the Q-learning. But this is a function, so I'm adding some parentheses. And now there is nothing more simple. The arguments we need to input are the predictions and the targets. So the predictions is of course our outputs, because that's the output of the neural network. You know, the output of the neural network is what the neural network predicts. So that's the prediction. So the first argument here is outputs. And then the second argument is of course the target, the thing we're trying to get. And it's already computed. Perfect. We can directly input target. Perfect. And now we have the loss. Just forgot a little t here. There we go. Now the warning should disappear. Yes, perfect. And now that we have the loss error, we can back propagate this error back into the network to update the weights with stochastic gradient descent. And that's exactly what we're going to do in the next step. So of course now what we have to do, as you might guess, is take our optimizer. Our optimizer, which again, we introduced here. We initialized it, and that's an Atom optimizer, which is actually an object of the Atom class, and it is already fitted with the parameters of our model, and we already chose a learning rate of 0.1%. So perfect, our optimizer is ready, but now we need to apply it on the loss error to perform stochastic gradient descent and update the weights. So when working with PyTorch, the first thing we need to do is reinitialize it at each iteration of the loop. We must reinitialize the optimizer from one iteration to the other in the loop of the stochastic gradient descent. And to reinitialize it at each iteration of the loop, well, we're going to use the following method, which is ZeroGrad. Here we go. ZeroGrad will reinitialize your optimizer at each iteration of the loop. Then let's not forget the parentheses. Perfect. And now that it is reinitialized, well, we can perform backward propagation with our optimizer. And how do we do that? Well, we take our TD loss and we are going to backpropagate it back into the network. And to backpropagate it into the network, we need to use the backward function. And inside this backward function, I recommend to input retain underscore variables and set it equal to true. I recommend to do this because this will improve backpropagation. The use of return variables equals true is to free some memory. And we need to free the memory because we're going to go several times on the loss. So that will definitely improve the training performance. And finally, last step of this learn function is to update the weights according to the backpropagation, that is, according to how much the weights contributed to the error. And to do this, we take our optimizer again, which was initialized and reinitialized, and we use the step function. And simply, with this line of code, by using the step function, this will update the weights. That's this line of code that updates the weight. This line of code backpropagates the error into the neural network, and this line of code uses the optimizer to update the weights. And there we go, we have a learning neural network. Alright, so congratulations. This was probably the most technical and difficult part of all this deep Q-learning model. I know PyTorch can be tricky sometimes with these unsqueeze and squeeze, but in the end I promise you will get a very functional neural network and therefore deep Q-learning model and eventually a great artificial intelligence. So now let's move on to the next step, of our deep Q-learning model, which will be the update function that will obviously update when the AI will discover the new state. So it will discover the new state, and then it will receive the reward depending on the action that it just played and this new state. So we will take care of this with the update function, and we'll do this in the next tutorial. Until then, enjoy AI!